Welcome to Research Rundown. Today we're diving into a fascinating study on machine learning and type systems in programming languages. Joining me are two esteemed experts with differing perspectives on this innovative research. Renowned for her work in pluggable type systems, is here to share her optimistic view on the potential of automatically inferring type qualifiers using graph transformer networks. On the other side, we have Professor, a seasoned analyst and critic of emerging technologies. He's brought his skeptical lens to examine the claims made by this research and will challenge Dr. S' enthusiasm with tough questions about scalability, reliability, and real-world applicability. In this episode, these two experts will engage in a lively debate, dissecting the findings of this paper and exploring its implications for the programming languages community. Let's get started and see how their discussion unfolds.
I'm thrilled to share my thoughts on this groundbreaking research. The authors have made a significant contribution to the field of programming languages and type systems by exploring the application of machine learning to infer pluggable types automatically. This study has the potential to revolutionize the way we approach code quality, and I'm excited to dive into its key findings. Firstly, the paper demonstrates that using machine learning to infer pluggable types can indeed improve code quality by lowering warnings in legacy code bases. This is a significant advantage, as many existing codebases are plagued by incorrect or missing type annotations, leading to a plethora of warning messages that can be difficult to navigate. By leveraging machine learning models, such as the Graph Transformer Network (GTN) model presented here, we can automate this process and reduce these warnings, making it easier for developers to focus on writing high-quality code. The authors' proposed NAPAST representation is a crucial component of their approach, allowing them to effectively encode minimal data flow hints for type qualifier inference. This representation enables the GTN model to accurately capture the relationships between variables and functions in the code, leading to better performance in inferring type qualifiers. I'm impressed by the author's creativity in designing this representation, which has been shown to be effective in encoding the necessary information for accurate type qualifier inference. Furthermore, the study highlights an important consideration for machine learning model training: the trade-off between data size and overfitting. The authors found that a surprisingly small dataset of around 16K Java classes is sufficient for good performance, beyond which overfitting becomes a concern. This finding has significant implications for practitioners looking to deploy similar models in real-world settings. In conclusion, this research demonstrates tremendous potential for improving code quality through the application of machine learning to infer pluggable types. By leveraging advancements in deep learning and data representation, we can automate tasks that were previously tedious and error-prone, freeing up developers to focus on higher-level concerns. The future of programming languages and type systems is bright indeed, and I have no doubt that this study will inspire a new wave of research into the application of machine learning to software development.
Fascinating perspective from Dr. Now let's hear Professor Marcus W.'s analysis of this research.
I'll begin by stating that I have reservations about the claims made in this paper regarding the use of machine learning for inferring pluggable type qualifiers automatically. While the author's enthusiasm is understandable, I believe it's essential to approach these findings with a critical eye. One concern I have is that the evidence presented to support the claim that machine learning can be used to infer pluggable type qualifiers automatically is, in my opinion, weak. The authors rely heavily on a single model, the Graph Transformer Network (GTN), which achieved impressive results on a specific dataset. However, this study lacks robustness analysis, which I believe is crucial when applying these findings to real-world scenarios. In particular, I'm concerned that the GTN model might not be resilient to changes in the programming language, dataset size, or domain-specific requirements. The authors seem to assume that their NAPAST representation can effectively capture all relevant data flow information, but this assumption may not hold true in more complex or dynamic environments. Furthermore, I worry that the model might overfit the training data, leading to poor performance on unseen data or in real-world scenarios. The authors mention addressing overfitting by using a large number of classes, but they fail to consider other factors that could contribute to this issue, such as model architecture, hyperparameters, or data preprocessing. Additionally, I think it's essential to acknowledge the limitations of this study. For instance, the authors may overlook the complexity of real-world programming tasks and the nuances of type qualifier inference. They might also neglect differences in code quality, maintainability, or readability among the Java classes used in their analysis. To be convinced by these claims, I would need to see more rigorous evidence, such as extensive robustness analyses, thorough comparisons with other models and approaches, and a deeper exploration of the factors contributing to overfitting. Furthermore, I'd like to see the authors address potential biases in their dataset and methodology, as well as provide more insights into how their findings can be generalized to real-world programming tasks. Ultimately, while this research presents some intriguing results, I believe it's essential to approach these findings with caution until more robust evidence is presented.
As we wrap up today's research rundown, let's take a moment to reflect on the lively debate between Dr. regarding their paper on using machine learning to infer type qualifiers in programming languages. The crux of their discussion centered around the potential of this research, with Dr. emphasizing its groundbreaking possibilities for pluggable type systems. Raised concerns about the methodology and evidence presented, highlighting the need for more rigor and validation. While these perspectives may seem at odds, it's essential to acknowledge that both have merit. Cutting-edge research often pushes boundaries, inviting new ideas and critiques. The tension between innovation and scrutiny is a hallmark of this type of inquiry. I want to thank Dr. for engaging in this thoughtful discussion, and I'm grateful to our listeners for joining us on this Research Rundown episode. We'll be back next time with another fascinating topic and lively debate. Until then, farewell.